Hello friends, welcome to this class of maths. Today we are going to look at probability. So what exactly is probability? It's one of those words that we normally use in our daily lives. We always say, no, I have a good probability of passing the exam. So what do we actually mean by probability? So probability is basically something like a chance. What is the chance that something happens? Mathematically, we call it probability. So let's look at the technical definition of probability. Probability is a way to quantify the likelihood that an event will occur. So we are talking about an event here, the probability that I pass. So my passing is an event. So we are talking about an event here, and I am talking about a number that I call probability that defines how likely that event is going to happen. So probability quantifies the likelihood that an event will occur. How do we get to a number? Probability of an event E is number of favorable events divided by the number of total events. Right, let's look at an example. What is the probability of getting one ace when a card is withdrawn from a pack of well shuffled 52 cards? So what are we looking for? We need an ace. How many aces do we have? We have 4 aces in a pack, right? So this is the number of favorable events. That means we actually find an ace. What is the total number of events? In how many different ways can we pick one card? So there could be 52 different outputs, right? So the probability of getting an ace is going to be 4 by 52. 4 is the number of events in which I get an ace, and 52 is all number of events. So the probability is 1 by 30. So as you will see, to find out any probability, you will basically have to find out the total number of events that are favorable for a particular event and the total number of events including these events. Some basics about probability. Probability lies in the range 0 to 1. This is very straightforward. Why does it lie between 0 to 1? Now, let's say the sun rises in the west. What is the probability of this statement? This event is never going to happen, right? So that means there are only 0 ways in which it can happen, and then the probability divided by anything. 0 divided by anything is always going to give you 0. So probability of sun rising in the west is going to be 0. The probability of a sure event, probability that sun rises in the east. There is only one way, right? So probability of sun rising in the east is 100%. That is 1 by 1, which is 1. Correct? So events that have probability 1 are called sure events, and events that have probability 0 are called impossible events. Let's move to this concept, probabilities of A and or B. So now we are talking about two events where we have A as an event, something happens, B as another event, something else happens. Now if A and B are events, the probability of obtaining either of them is probability of A or B. Either means one or the other, or it could be both also. So A or B is equal to probability of A plus probability of B minus probability of A and B. Now the easiest way to understand this concept is looking at the Venn diagram. Let's say I have this Venn diagram. This represents A, this represents B. So I want to make sure that I get this region A or B. That means I am choosing a point and I am just finding out how many points I have within this region, A or B. So you will see that it includes A, it also includes B, and the tricky part here is that this particular region that is common to A and B, that is being included twice, right? It is also included in A, it is also included in B. So if you actually want to find out what the area of this A or B, you'll have to subtract this much part once, right? So that means what we end up getting is A plus B minus A intersection B. So the same logic is applied here. Probability of A or B is equal to probability of A plus probability of B minus probability of A and B. You will see that in a lot of probability questions this Venn diagram approach is really helpful. So let's look at this particular question now. A high school consists of 25% juniors to 15% seniors and the remaining 60% are of other grades. Since no student can be both junior and senior, the probability of student being a junior or senior is 0.25 plus 0.15 is equal to 40%. Now if you draw the Venn diagrams, you will see that this is juniors, this is seniors and this is others. These are distinct sets because there cannot be a student that belongs to more than one of these categories. So this is juniors, this is seniors and this is others. So that is why when we talk about the probability of student being junior or senior, what we do is probability of being a junior plus probability of being a senior minus probability of being a junior and also a senior. Now this probability is 0, correct? It's not possible, it's an impossible event. So we only add these two, and 15% plus 25% we get 40%, straightforward. When A and B are independent events, probability of A is going to be probability of A into probability of B. Sorry, probability of A and B is going to be equal to probability of A and probability of B. Now this is similar to what we have seen in the permutation and combination class. What we have seen is fundamental counting principle. If there are n ways of doing something and there are m different ways of doing something else, the total number of ways we can do both the things is n into m. Now we have also seen that whenever we are talking about and, we do a multiplication. Whenever we are talking about or, we do an addition. So the same thing applies here also. We are talking about A and B, and A and B are independent. So probability becomes A probability of A into probability of B. Let's look at an example. We have two dice. A is the event that 6 shows on the first die and B is the event that 6 shows on the second die. Now these two events are independent, right? Because we are dealing with two different dice. So these are independent events. So if both dice are rolled at once, the probability of 2 6s. Now 2 6s means A is also 6, which is probability of A is going to be 1 by 6. There is only one way in which you can get a 6, whereas there are 6 total number of ways. Probability of B is also going to be 1 by 6, correct? With the same logic. So probability of A and B, that means I get a 6 on the first die, I also get a 6 on the second die. So probability of A and B is going to be probability of A into probability of B, which is going to be 1 by 6 into 1 by 6 is equal to 1 by 36. So these are two fundamental concepts you need to remember with respect to probability. If if A and B are events, the probability of obtaining either of them, probability of A or B, is equal to probability of A plus probability of B minus probability of A and B. And if A and B are independent events, then probability of A and B is going to be probability of A into probability of B. So just to recap, Venn diagrams. When we are talking about an event, let's say this is, let's say, a universal set, right? Universal set is always going to have probability of 1, correct? We are talking about this event. A happens, it is this portion. A doesn't happen, it is this portion. So the A doesn't happen is shown by A dash. So you will see from the Venn diagram that probability of A plus probability of B, probability of A plus probability of A dash is going to be equal to 1. Either A happens or A doesn't happen. So both these combined will always give you 100%. Mutually exclusive, if these two events are mutually exclusive, they don't have anything in common, the probability of A and B is going to be 0. Right? Again, it is clear from the Venn diagram that you are selecting a point here which is there in A also, which is there in B also. There doesn't exist any point, so probability is going to be 0. Probability of union, probability of A union B. We have seen this in the last slide. It is probability of A plus probability of B minus probability of A intersection B. Intersection is shown like this on the Venn diagram. This is the probability of A and B. And if A and B are totally independent events, what we get is probability of A into probability of B is equal to probability of A intersection B. Let's move on to this concept of 1 minus x probability. If two events A and B are collectively exhaustive, that is, what do you mean by collectively exhaustive? That means when they are combined together, when they are collected together, they are exhaustive. That means they represent the entire sample space. When added, they cover the entire sample space. For example, either I wear black shoes or I don't. So A is the event is I wear black shoes, and B is an event I don't wear black shoes. Right? Now these are collectively exhaustive cases. Either I will wear or I will not wear. So when we are talking about two such events that are collectively exhaustive, the probability of A and probability of B added is going to give me 100%. Correct? This is what we saw in the Venn diagram also. There what we had is, this is A, outside A dash, this is the entire sample space. So A plus A dash, if you combine, you will get the entire sample space. So probability of A plus probability of B is equal to 1. And probability of A can also be defined as probability of 1 minus probability of B. Also probability of B can be written as 1 minus probability of A. Most common use of 1 minus x probability is when we are talking about probability of none of something, we write it as probability of 1 minus probability of at least one of something. Let's look at an example to get this point very clear. In a group of 5 boys and 4 girls, 2 children, this is R, 2 children are picked at random. What is the probability that at least one of them is a boy? So wherever we deal with at least one, right? Think of it this way. I need at least one boy. So that means I am talking about an event that where I have at least one boy. That means I am talking about all events minus all events where I have no boy. Correct? At least one boy means all events minus number of events where I have no boy. So that is, so probability of at least one boy is equal to probability of probability of at least one boy is equal to 1 minus probability of no boy. Correct? And what is going to be probability of no boy? Probability of no boy means all girls. That means all 2 children, both the children are girls. How many ways can I pick them? 4C2 ways. What is the total number of ways I can pick 2 children from 9 children? 9 is 5 plus 4. That is 9C2. So this becomes probability of no boy, and I need 1 minus probability of no boy. So I get this as the probability of at least one boy. The probability of at least one boy is 1 minus probability of no boy, which is probability of all girls. This is the probability of all girls. The answer is 5 by 6. Let's look at practice problem 1. Please pause the video and give it a try. So we have a leap year here. We have 366 days, which is basically 366 divided by 7 means we have 52 weeks plus 2 extra days. Correct? So 52 weeks are anyway going to have 52 Sundays, right? And we are going to get the 53rd Sunday depending on where these 2 days fall. Correct? Now let's look at this. Let's look at the calendar. Thursday, Friday, Saturday, Sunday. Let's say 1st January of any particular, or rather this particular year, starts on Monday. 1, 2, 3, 4. This is how the calendar is going to go, right? If you continue it all the way till 364th day, what we are going to get is 364 is going to fall here, 363 is going to fall here, 362 is going to fall here, that way, right? Correct. Now the next 2 days are going to be Monday and Tuesday, at least in this specific example, 365 and 366, because we are dealing with the leap year. Correct. Now we need to find out these 2 days probability of either of these 2 days being a Sunday. Correct. In how many ways can this happen? See, it can happen when the year is starting. That means the 1st January of that year is starting. If it is starting on Monday, then we are going to have these are 52 days. So we are going to have only 52 Sundays. So if it starts on Monday, we are going to have only 52 Sundays. If it start on Tuesday, then we are going to have only 52 Sundays again. Wednesday also 52 Sundays, because the 2 extra days are going to fall on Wednesday and Thursday. Here also 52 Sundays, here also 52 Sundays. Now if the 1st January falls on a Saturday, so the remaining 2 days are going to be Saturday and Sunday, in which case we'll get 53 Sundays. If it falls on Sunday, 1st January falls on Sunday, we are going to get Sunday and Monday as 2 extra days. So here also we'll get 53 Sundays. So you look at it, we have 7 different cases depending on when the 1st January, where the 1st January falls, and out of those 7 cases, 52 Sundays happens in 5 out of 7 ways, and 53 Sunday happens in 2 out of 7 ways. So these are the probabilities. 54 Sundays, just look at it, 54. Obviously looking at here, you will know that 54 Sunday is not possible. Another way to figure that out is 54 into 7 is going to be 371 days. We'll need 370 days minimum, but whereas we have only 366 days, right? So that means 54 Sundays is not going to happen in 1 year. So the answer is 5/7 for 52 Sundays and 2/7 for 53 Sundays. Let's look at this problem. Please pause the video and give it a try. Probability that A will shoot a target is 1/3. Probability of B will shoot the target is half. Probability of A is 1/3. Probability of B is half. Right? What is the probability of A hits, B doesn't? Now we are talking about this event. A hits and B doesn't hit. So I am talking about probability of A hits and B doesn't hit. Correct? So what is probability of A? Probability of A 1/3. B doesn't hit is going to be 1 minus B hits, which is going to be again half. So 1/3 into 1/2 is 1/6. So this is 1/6. Both hit. I am talking about A hits and also B hits. So since there is an and, I multiply. So what I get is 1/3 into 1/2 is 1/6 again. None hits. None hits means A doesn't hit. A doesn't hit into B also doesn't hit. Correct? So that is going to be A doesn't hit is 2/3. B doesn't hit, it is half. So probability of both not hitting is 1/3. Correct? The target is hit. Now this is interesting. The target is hit. I'm not worried about who hits the target. I'm just ensuring that the target is hit. That means target is hit means 1 minus target not hit. Correct? That is going to be same as target not hit is same as none hits, right? So this is going to be 1 minus probability of none hits is 1/3 as we have found out here. So here I'm going to get 2/3. Another way to do that is figure out in what ways this can happen. target is hit. Targeted hit means A hits and B doesn't, or B hits and A doesn't, or A and B both hit the target, right? So let's find out. This way also you should get the same answer. Probability of A into probability of B doesn't hit, that means 1 by 3 into half, plus B hits half, A doesn't hit 2 by 3, A and B both hit, which is 1 by 3 into 1 by 2. Let's figure it out. So this is 1 by 6, this is 1 by 3, and this is also 1 by 6. So it is basically 1 by 6 plus 1 by 6 plus 1 by 3, which ultimately comes out to be 2 by 3. So it's the same answer. Either way you do, you will get the same answer. None hits. Okay, it's the same as, sorry, this is repetitive. This is the same problem. Exactly one hits. Now what is exactly one hits? Exactly one hits means A hits, B doesn't, or B hits, A doesn't, right? A hits and B doesn't, or B hits and A doesn't. So that is going to be 1 by 3 into B doesn't hit is 1 by 2, plus B hits is half, A doesn't hit is 2 by 3. So that is going to be 1 by 6 plus 1 by 3, which is again 1 by 6 plus 2 by 6, which is 3 by 6, which is half. So exactly one hits is again half. At most one hits. At most one hits means 1 minus, okay, at most one hits means again it is either A hits, B doesn't, or B hits, A doesn't, or A doesn't hit and B also doesn't hit. Correct? So that is going to be 1 by 3 into B doesn't hit half, plus B hits, A doesn't hit is 2 by 3, A doesn't hit, B also doesn't hit. So what you're going to get here is, this is 1 by 6 plus 1 by 3 plus 1 by 3. So that is 1 by 6 plus 2 by 3, which is 1 by 6 plus 4 by 3. Sorry, 1 by 6 plus 4 by 6, which is going to be 5 by 6. Correct? So this probability is going to be 5 by 6. Another way to solve this, at most one hits is also can be written as 1 minus both hit. Correct? At most one hits is 1 minus both hits. So what is both hits? Both hits probability is 1 by 6. Right? So at most one hits is going to be 1 minus 1 by 6, which is again going to be 5 by 6. So I recommend you pause the video and go through these examples again, and these examples will make your concepts more clear. Let's look at this problem. Please pause the video and give it a try. A has half probability of scoring the 99th percentile on the GRE. How many times should he appear to have more than 90% probability of scoring the 99th percentile at least once? Okay, now this is at least once, so you will have to employ one tactic that we have learned, 1 minus none. Okay, now what is this 99 percentile? See, if you look at this 99 and this 90% here, there is a possibility that you will get confused. So let's reword this problem. What we say is A has 1/2 probability of passing. Forget about this 99 percentile. Correct? Now let's reword the same problem. A has 50% probability of passing the GRE. How many times should he appear to have 90% probability of passing? At least once. I'm just changing the scenario in order to get rid of this confusing 99 percentile. Okay, so now A has 50% probability of passing. So every time he takes a test, he has equal chances of passing and failing, right? So now he says, okay, now you will see that two times he takes the test and he fails both the times, that probability is going to be, he fails in once first time, he also fails the second time, so that is going to be 1 by 4, means 25%. He takes the exam 3 times, let's say, he doesn't and he still doesn't pass, that probability is going to be, he fails in the first time, fails in the second time, fails in the third time, so that is going to be 1 by 8, which is 12.5%. so the more number of times he takes, his probability of failing in all the three, or rather his probability of failing is going to reduce, right? So that is why he decides to take the GRE more number of times, but now he wants to make sure that at least he has 90% probability of passing at least once. He wants to pass at least once with a 90% probability, correct? So we know, let's look at this. We'll employ the tactic that we just saw. We say probability of at least once passing is equal to 1 minus probability of failing all the time, correct? So let's say we're talking about an number n and he has taken the GRE n number of times. Okay, if n is equal to 1 and n is equal to 1 and probability of failing all the times, that means one number of times, is going to be 50%, correct? That is already given. If n is equal to 2, the same probability of failing at all times, that means failing both times, is going to be 50% into 50% is going to be 25%. N is equal to 3, probability of failing all times is 50% of this again, which is equal to 12.5%, correct? N is equal to 4, probability of failing all times is going to be 6.25%, right? Let's look at probability of at least one passing. Probability of at least one passing is going to be 1 minus probability of failing, right? So probability of at least once passing is going to be 1 minus this is here, in n equal to 1 is going to be 50%, n equal to 2 it is going to be 75%, n is equal to 3 it is going to be 87.5%, and n is equal to 4 it's going to be 93.75%, correct? And what do we need? We need more than 90% probability. So as n increases, we see that his probability of passing at least once is increasing, but we want to make sure that he has 90% probability or more than 90%. So you will have to wait till the fourth pass for this probability to be more than 90%. So here the answer is, he will have to take the test 4 times in order to make sure that he has 90% probability of passing at least once. Rewording the same thing and putting this scenario in place, we'll say that A has to take the GRE 4 times in order to ensure that he has 90% probability of scoring 99 percentile at least once. So be very careful about reading the question. There will be some information that you can reword, there will be some information that is confusing but not necessary in solving the problem. So be very careful while reading the question. Let's look at this one. Please give it a try. In a group of 100, 30 drink only tea, 20 drink only coffee, and 15 drink only mocha. 5 drink neither of the 3 and 10 drink all 3. What is the probability that a person picked at random drinks exactly 2 of the 3? Okay, the simplest way to do it is form a Venn diagram. So we have 3 drinks, standard case of Venn diagram. Okay, we have these 3 drinks. So one is tea. 30 people drink only tea. That means this is 30. I'm not including these 3 regions here. 1, 2, 3. I'm not including these. This is only tea. So he doesn't eat, this is tea, this is coffee, this is mocha. So these 30 guys don't drink coffee nor do they drink mocha. So it is all the part of tea, that is only tea, right? 20 drink only coffee, so this region is 20. 15 drink only mocha, so this region is 50, right? Now we need numbers for these areas, these 4 areas. 5 drink neither of the 3. That means out of these 3 circles we have 5 people. Okay. 10 drink all 3. So this tiny guy here is 10. All 3. Okay. And we have, let's say this is X number of people, this is Y number of people, this is Z number of people. Okay. So and all of these people have to amount to 100. So what do we get? So we have 30 plus 20 plus 15 plus 5 plus X plus Y plus Z should be equal to 100. So let's get X plus Y plus Z. X plus Y plus Z, this is 50 plus this is 20, 70. So X plus Y plus Z is going to be 100 minus 70 as 30. So there are X plus Y plus Z together are 30. That much we know. Okay. Now let's address the question. What is the probability that a person picked at random drinks exactly 2 of the 3? So exactly 2 of the 3, you know which region we are talking about? We are talking about this region. We are talking about this region. We are talking about this region. We are not talking about these 10 guys because it is exactly 2 drinks. It's not at least 2. It is exactly 2. That means we are talking about people who drink only tea and mocha, or tea and coffee, or coffee and mocha. We are not including guys that drink all the 3. So that is, again, interestingly, it happens to be X plus Y plus Z number of guys we have who fit in this definition of exactly 2. Out of that, we this is number of guys out of 100, correct? So we are basically looking out at this probability. So that is going to be X plus Y plus Z divided by 100. That is going to be 30 divided by 100 equal to 30%. So there is 30% probability that a person picked up random drinks exactly 2 of the 3. Let's look at this question. Please pause the video and give it a try. 5 boys and 5 girls have to be seated in a row. Find the probability that all boys are together and all girls are together. Okay. So we have 5 boys. 1, 2, 3, 4, 5. 5 girls. 1, 2, 3, 4, 5. Okay. To be seated in a row. So what is total number of ways we can seat them? It's going to be 10 factorial. 10 people, it's 10 entities to be arranged in a row. It's going to be 10 factorial. Correct? Find the probability that all boys are seated together and all girls are seated together. So the probability of all boys are seated together and all girls are seated together, there are only 2 such cases where we have all boys sitting together 1, 2, 3, 4, 5 and all girls like this, or all girls like this and all boys like this. There are only 2 ways. So we have 2 ways in doing that. Each of those ways we haven't yet looked at the sitting arrangement for boys. They themselves can sit among themselves in 5 factorial ways. Same, girls can sit among themselves in 5 factorial ways. So these are total number of ways we are talking about out of the total 10 factorial ways. So probability is going to be 2 into 5 factorial into 5 factorial divided by 10 factorial. That is going to be the answer here. I'll just write it here. 2 into 5 factorial into 5 factorial divided by 10 factorial. No 2 boys are together. So no 2 boys are together. So that means there is no restriction on girls. So first I ask girls to sit 3, 4, 5 and I ask boys to sit, take these positions adjacent to the girls 1, 2, 3, 4, 5, 6, right? So these girls now can be arranged in 1, 2, 3, 4, 5 factorial ways, and guys, 5 guys can take 5 seats among these 1, 2, 3, 4, 5 and 6. There are 6 seats available. 5 guys can take 5 seats and 1 seat can be left empty. So there are 6 seats for 5 boys to choose from. So this is the number of ways in which this arrangement can be completed, and the total number of ways is 10 factorial. So this is the probability of no two boys are together. So that is going to be 5 factorial into 6c5 divided by 10 factorial. Let's look at the third case. Two particular boys are always together. Now if two boys are always together, let's look at this. If two boys are always together, they act as one entity, right? And other people are free. There is no other restriction on others. So how many entities do we have to fit? We have to fit these two guys act as one entity. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 entities to fit. So that can be arranged in 9 factorial. And between these two boys, they themselves can be fit in 2 factorial ways. So this is the total number of arrangement we can do, divided by number of arrangement with no restriction. So this is the probability of two particular guys are always together. So that is going to be 9 factorial into 2 factorial divided by 10 factorial. Let's look at the fourth one now. Two particular girls are never together. So two particular girls are never together is 1 minus probability of two girls always together. Correct? Two particular girls are never together is equal to 1 minus two particulars are always together. So what is that going to be? Probability of two girls always together is the same as probability of two boys always together, which is same as this. Correct? So that is going to be, the answer here is only 1 minus 9 factorial into 2 factorial divided by 10 factorial. Let's move to the next one. Please give it a try. Letters of word typhoid are shuffled to form all possible words and a word is selected randomly. What is the probability that P comes before H in the chosen word? Okay, so first of all, how many ways can we arrange the words of typhoid? So it's going to be 1, 2, 3, 4, 5, 6, 7. It's going to be 7 factorial ways, right? Is there any repetitions? There are no repetitions here. That means I coming twice or O coming twice. So we are not dividing it by anything, right? So the total number of ways is 7 factorial. Now how do we figure out this part? Probability of P comes before H. P can come before H, where P is in first position, H could be anywhere, or P could be in second position. In that case, H will have to be third position, fourth position, fifth position, that way. So this is going to be very complex to do, but if you look at it, either P will come first or H will come first. They both cannot come at the same location, obviously, right? So either P will come first or H will come first, and we are talking about all the 7 factorial type of arrangements. So in half of these arrangements, P is going to come first, and in half of the other arrangements, H is going to come first. In fact, they know the ones in which P comes first and the ones in which H comes first, these are going to be mirror images of each other, in the sense that if we swap P and H, you are going to get one set from the other set, right? So that means number of such cases are same. That means they and both of them amount to 7 factorial ways when added. So that means number of ways in which P comes first is 7 factorial divided by 2. So that is the number of ways in which P comes first divided by the total number of ways. So the probability is half. Right? Mathematically, it is going to be very difficult to arrive at this number in the numerator, in how many ways P comes first, right? Out of those 7 factorial ways. That's going to be very complex. But we know that P is going to come first half of the times. So that is going to be half of 7 factorial divided by 7 factorial, which is half. Now let's look at this one, an extension of the earlier problem. Please give it a try. Same words, same letters, typhoid word, letter of words, typhoid need to be arranged. We have seen that it can be arranged in 7 factorial ways. What is the probability that P comes immediately before H in the chosen word. Okay, how do we go about this? Now P comes immediately before H. So let's say we have seven letters, right? 1, 2, 3, 4, 5, 6, 7. So either P, H and some letters here, or it's going to be P, H and some letters here, or it is going to be P, H and some letters here, or it is going to be P, H and some letters here, or it is going to be P, H, or it is going to be P, H. Correct? So there are how many? 1, 2, 3, 4, 5, 6. 6 ways in which this can hold true. 6 ways, in fact, into these 5 can have their own arrangements. So that is going to be 5 factorial. Correct? So 6 times special cases. Each of those 6 cases will have 5 factorial ways divided by the total number of ways will be 7 factorial. So that is going to be 6 into 7 into 6, 5 factorial will get cancelled. So that's going to be 1/7, 1/7 probability. Let's look at this one. Please give it a try. In a group of 10, 4 people have 3 siblings each and 6 people have 1 sibling each. Okay. Now we have 10 people. 3 people have 6 siblings. 4 people have 3 siblings each. So let's draw 3 siblings each. 3 siblings each itself means that we are talking about this group of children as one family. Each of them has 3 siblings. Correct? So this 4 kids already we are talking about here. 6 people have 1 sibling each. 1 sibling each means we are talking about a couple of children from the same family. These happen to be siblings of each other. These are 2 children. Again, these are 2 children, and we have 6 sub children. That means we'll have to have 3 pairs of siblings, right? And if you add them up, 4 plus 2 plus 2 plus 2, this is going to give us 10. Correct? So this is the only possible combination wherein in a group of 10, 4 people have 3 siblings each and 6 people have 1 sibling each. So we already have the layout now. So let's look at the problem. If 2 are picked randomly, what is the probability that they are siblings? So that means 2 are picked randomly, and they need to be siblings. That means either they are picked from here, or they are picked from here, or they are picked from here, or they are picked from here. Right? So we have 4 different events. This plus this plus this plus this. That will give us the answer. Right? So what is the probability that we end up selecting 2 children from this group? So number of ways in 2 children can be selected in this group itself is going to be 4C2 divided by total number of ways we can select children. Correct? What is the probability that 2 children are selected from this group? That is going to be 2C2, which is basically is going to be 1 divided by 10C2. Right? Here again 2C2 by 10C2 plus 2C2 by 10C2. So basically what we are saying is the probability is going to be 4C2 divided by 10C2 plus 4C2 plus 3 divided by 10C2. This is the probability of both children being siblings. Let's look at this one. Please give it a try. 10 different chocolates are distributed among 5 children. What is the probability that one of the 5 children gets all the chocolates? Let's look at the 10 different chocolates. Right? So we have these chocolates, and we have these sets as children. What we are trying to do is these 10 different chocolates, we'll have to distribute in these 5 buckets, right? So how many options does this first chocolate have? It has 5 options to go to. This chocolate also has 5 options to go to. This chocolate also has 5 options to go to. Like that, all the chocolates have 5 options to go to. So that means the total number of ways we are talking about is 5 raised to 10. 5 options for every chocolate, 10 such chocolates, we are talking about 5 raised to 10. Correct? That is the total number of distributions. Out of those, now we need to find out the probability of one of the 5 children getting all the chocolates. That means either first child gets all the chocolates, or the second child gets all the chocolates, or the third child gets all the chocolates, or the fifth child gets all the chocolates, fourth child gets all the chocolates, or fifth child gets all the chocolates. In how many ways can we have all the chocolates going to the first kid? There's only one way that all the chocolates goes to the first kid, right? That way is this goes to first child, this chocolate goes to second child, this chocolate goes to third child. So there's only one way in which this can happen. Similarly, there is only one way in which this can happen. Only one way this can happen. Only one way this can happen. Only one way this can happen. And these are all, alternatives to each other, in the sense that one of the five children gets all the chocolates. The probability of that is going to be probability of A getting all the chocolates plus probability of B getting all the chocolates plus this plus this plus this. So the whole total number of events we are talking about here is 5. We just add them. Correct? So the probability is going to be 5 divided by 5 raised to 10. It's going to be 1 divided by 5 raised to 9. This answer here is 1 divided by 5 raised to 9 is the probability of one of the 5 children getting all the chocolates. No child gets no chocolate. No child gets no chocolate is the same as saying that every child gets at least one chocolate. Correct? Every child gets at least one chocolate. So if I want to ensure that every child gets at least one chocolate, what I'll do is first I'll give one chocolate each to each child and then distribute the pending ones. Correct? So logically the step would be, first of all I select out of this 10 chocolates, I select 5 chocolates, then I give them to 5 different kids. That is going to be in 5 factorial ways. Correct? Or you can simply write it as 10p5 also. So I take out of 10, I select 5 chocolates and distribute it to 5 children. 10c5 into 5 factorial or 10p5, and then from the remaining chocolates, that are 5 remaining chocolates, I just assign them randomly. So the first chocolate in that will have 5, same argument here. First chocolate will have 5 options to go to, second will have 5 options to go to, third will have 5 options to go to, like that the pending 5 options. So that means it's going to be into 5 raised to 5. That is the total number of chocolate arrangements we can have, divided by, again what we have seen is total number of arrangements of 5 raised to 10. So this is the probability of no child getting no chocolate. So with that, I thank you for watching the video. I hope you learned a good deal about probability, and I look forward to meeting you in the next class. Thank you.